Mathematics, how much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from that.
Good morning, grade 12s. Welcome back. Hope you had a good day yesterday. Today is Wednesday, April the 15th. And I just want to start today by sharing with you a verse of the day again. Yesterday's verse of the day encouraged us to find ways which we could practically love one another. And today's verse of the day goes along with that. It is from Philippians chapter 1, verses 9 and 10, where it says, "And this is my prayer, that your love may abound more and more in knowledge and depth of insight, so that you may be able to discern what is best and may be pure and blameless for the day of Christ." And so that is our prayer, that our love would abound more and more in knowledge and depth. Love for Jesus, love for one another, and prayer is also our prayer that we'll be able to discern what is best and how to show and practically show that love to one another. And so I want to encourage you to continue to do that. Reach out, show love to one another, and continue to connect with one another. It is time for us to gather together on a video chat, and so I want to do that on Thursday at 11 a.m. I'll email you out a link to a Zoom video conference, and I'll put that link on Connect as well. But Thursday at 11, try to keep it open, and it would be great if we could have everybody involved in that. We could see each other once again, you can ask some questions, and we can just actually see one another again. And so if you can't make it for whatever reason, that's not a problem, but maybe just email me and let me know that you're not going to participate, so we're not waiting on you. All right, you've been working on a review over the last couple of days, and I want you to continue working on that today. We'll give you one more day to work on that. But in the meantime, today there were a couple of questions that were asked on it over the last couple of days, and so I'm going to go and do a couple of questions on the whiteboard for you, and you continue working on it. On Thursday's class, in addition to the video chat, I'll put a video up with some notes that will be on our final section of this, which will be collisions, and it'll just be one simple day of collisions. And then we're going to have a test on this unit. So the test will primarily be on the review that you've been working on, with maybe one question out of collisions that we'll look at on Thursday. And then next week we'll move into a different unit. So let's go over to the whiteboard and let's take a look at a couple of the questions that were asked. So the first question that was asked was question number 38 off this review sheet, and I'll just read it to you, and then I've got the question on the board and we'll walk through it together. It says a 35 kilogram box needs to be lifted to the top of a loading dock, which is also accessible by a ramp. The ramp is 5 meters long, has a vertical height of 1.7 meters. Question A says, what is the minimum force required to lift the box straight up onto the loading dock? Well, to lift up anything, minimally we have to overcome the force of gravity. So again, we know force of gravity is mg, 35 kilograms, 9.8 newtons per kilogram, 343 newtons. Again, textbook will put this into significant digits of 340 or 3.4 times 10 to the 2 newtons. All right, part B says, what minimum amount of work is required to lift the crate straight up onto the loading dock? Well, again, we know work is force times distance. The force is the 343 newtons we just found. The distance it has to be lifted is 1.7 meters, giving us 583 newton meters, or 5.8 times 10 to the 2 newton meters. Okay. Now, part C is where we have to do a little bit more work on this. Part C now says we want to push the box up the ramp. All right, and so to push a box up a ramp, again, we have to overcome the force that is pulling the box down the ramp. And so if I set up this triangle here, we've got our box on our ramp, we'll have the force of gravity acting straight down, we'll have this force here, which is the normal force, didn't label it, there it is, we don't need it, but normal force. And then we will have what I've called an FF for friction. It's not really a friction force because there's no friction in the question, but I'm calling it a friction force because it is a force that is opposing the motion, right? We're pushing this up, and that upward force along the slope I've called FA for the force that we are applying to this box to push it up. The FF and the FA have to equal in order to get that box moving up the slope. The one thing that's not given to us is the angle, but we can find the angle. So in this diagram, this triangle here, I've drawn our ramp. It's got a height of 1.7. The ramp is 5 meters long, and that allows me to find the angle using right angle trigonometry. And so the angle is 20 degrees. That 20 degrees goes into our triangle here, the bottom of the triangle. Now we need to find FF. So again, it's a right angle triangle. So sine of 20 equals FF over the 343. Giving us an FF of 117 newtons. And again, to push it up the ramp, we have to be at least equal to that 117 newtons. So our FA, the force that we need to push it up, is going to be that 117 newtons. I believe the textbook again, or this paper, had it as 120 newtons that we have to push up. So again, that's just rounding for significant digits. All right, let's go to the other board, and we're going to do question 74, one of my favorite questions because it deals with roller coasters. Here we go. Okay, here's our roller coaster question. Question number 74. Forgot my paper. Question 74 says that we have a roller coaster that looks like what I've drawn here. Again, you have it on the paper. It's much better, and your paper has heights listed in here. I'll talk about the heights. You've got them on the paper. All right, so this is our roller coaster, and it says we have a car, 1,000-kilogram cart, at rest at A. All right, and then this roller coaster car is going to up and down and end up stopping at, or just past F. So, question 8. At what point on the track is the car's gravitational potential energy the greatest, and where is it the least? Well, it's greatest, the gravitational potential is greatest where it is highest off the ground. So, greatest at A. Right? At point A here, it's the highest off the ground. Where the gravitational potential is the least is at the point where it is closest to the ground, and that happens at point F. So the answer to A is greatest at A, least at F. Now, part B and C we're going to do together because it's the same calculation. Now again, we've been talking about conservation of energy the whole time here in the last little while, and this is a classic conservation of energy question. Okay? At every one of these points, A through F, there is a total amount of energy. At point A, if it is at rest, at point A, it only has gravitational potential energy. At every other point along this track, this roller coaster car has both gravitational energy because it's off the ground, and it has kinetic energy because it's moving. Okay? And again, those total amounts of energy have to equal. So in part B, it says, what is the car's maximum speed? Well, it's going to reach its maximum speed where the kinetic energy is the greatest. And the kinetic energy will be the greatest where the gravitational energy is the least. Right? So that happens at F. So it reaches its maximum speed at F because, again, that's where the gravitational energy is the least. So what I've set it up here is the total amount of energy at A has to equal the total amount of energy at F. And again, these could be any letters, okay? It could be B and D, B and E, A and E. Doesn't matter. The total energy at all of the points are equal. But we're going to look at A, and we're going to look at F. All right? And we're going to look at A because we know a piece of information of A. We know that the cart is at rest. All right, so gravitational potential energy is the only kind of energy we have there. At F, we have kinetic energy and gravitational energy. So the total amount of energy is the sum of those two. Plugging in our formulas, mg height at A plus a half mv squared plus mgh at F. Mass cancels out, we don't need the 1,000 kilograms at this point. So we plug in our numbers, 9.8 times 80 equals a half v squared plus 9.8 times 5. Solve for v, we get 38 meters per second. Okay, now, because we recognize that the total amount of energy is the same at all the points, when we move to part C, where it says, what is the speed of the roller coaster at point E, all we're going to do is we're going to change this F to an E. We're going to change these F's to an E. And all that changes is this height. And so I've written here, change H to 62 meters, because that's the only change that happens is the height off the ground. And we'll resolve for V, giving us 19 meters per second. All right, so all we're doing is instead of using E total from A equaling E total F, we're now doing A to E. All right, move to part D. Part D is a kinematics / dynamics question. We want to find what constant force would be needed to bring this cart to rest 5 meters after it hits point F. So at point F, we know that its velocity is 38 meters per second. We just found one. We want to bring it to rest, so we want a V2 of 0, and we want to do that in 5 meters. So the first thing we're going to do is find what is the deceleration of this cart. So we have a formula, our V2 squared equals V1 squared plus 2AD formula. We're going to rearrange it to solve for acceleration, plug in our numbers, and you get an acceleration of negative 144.4 meters per second squared. To find the force, mass times acceleration. Okay, it's a frictionless track, it said earlier, and so the only force that's stopping it is the net force, and so that equals mass times acceleration. 1,000 times the negative 144.4 gives us negative 144,400 newtons, or as it says on the answer page, negative 1.4 times 10 to the 5 newtons. Okay, so that's how you do that question. I did have one other question on question number 78, I believe. We're going to save that question. I'm going to do that question in tomorrow's video before we move on. But I want you to give it a try. It is a question that uses energy. What you have to do in that question is use energy, elastic energy and kinetic energy, to find the speed, the velocity at which that human cannonball leaves the cannon at 45 degrees. Then you're going to set it up as a projectile motion question. Right? Along your hypotenuse, you're going to have the speed at which it's leading the cannon, 45-degree angle, you're going to find your horizontal velocity and your vertical velocity, and you're going to use that information to find the distance that human cannonball flies. Go back to your projectile motion questions and remember how to do projectile motion questions, and it will help you do question 78 if you had that question. I'm going to leave it at that for today. Tomorrow we'll come back and we'll look at question 78 and any other questions that you might have had, as well as look at simple elastic collisions, and we'll also meet at 11 o'clock for our video chat. Hope you have a great day today. We'll see you tomorrow.